The objective of this lecture is to provide two examples in particle kinetics where the particle moves while in contact with either a one-dimensional rigid curve or a two-dimensional rigid surface. The first example in this lecture is the following problem. A particle moves while in contact with a rigid curve in the form of a cardioid. The cardioid has the following equation. As the equation R is equal to B times 1 plus the cosine of theta. And there's a particle that's located on the cardioid, and the particle has mass m. Now, what's important about this problem is that the cardioid is actually affixed to a horizontal shaft. The shaft rotates about the horizontal direction with an angular velocity omega, as I will draw. So here's the horizontal shaft, and the horizontal shaft is fixed to the ground, which will be the inertial frame eventually in this problem. And the angular velocity of the shaft is omega. Point O is located at one end of the cardioid, and it's the point from which distances are measured, and point Q is located at the other end of the cardioid. I'm also going to assume in this problem that there's friction, but I'm not going to state ahead of time what type of friction. We're going to look at both types of friction. And in order to be able to make the problem a little bit more tractable, I'm going to assume that this angular velocity in magnitude is equal to a constant. Now, that's the setup. If you see, the objective of this problem, which is what we've been doing in other problems, is to determine the differential equations of motion for the particle in terms of the angle theta. Now, we're going to go about doing this problem in the following way. We know we have a particle sliding on a one-dimensional rigid curve. The curve itself rotates relative to the ground, and the ground is what's going to be taken as our inertial frame. So we have to apply Newton's second law. So we're going to need to apply Newton's second law, force equals mass times the inertial acceleration. But before I get into all that, I want to do a little bit of preliminary work here, because we're going to be using some of these results later on. So this is going to require a little bit of preliminary. So I'll call these preliminaries. And then we'll get into the details of the problem. So the first thing is that rather than carry around this equation b times 1 plus cosine theta and all of the associated derivatives, I'm first going to start by just differentiating this twice, and I'm going to use these two results later on in the expressions, and I'll actually show you how that actually works as we go through this. So the first derivative of r, or the rate of change of r, is minus b theta dot sine theta, and then the second derivative, r double dot, is minus b times theta double dot sine theta plus theta dot squared cosine theta. Now, in addition to that, I also want to use the following trigonometric identity, which I'm going to need later on in the problem. So we know that cosine of 2 alpha is equal to cosine squared alpha minus sine squared alpha. That's also equal to 1 minus 2 sine squared alpha, which is equal to 2 cosine squared alpha minus 1. So from this, I get this identity that 1 plus cosine of 2 alpha is equal to 2 cosine squared alpha. I'm going to need that later on when I actually do some of the calculations that we're going to need in order to get to deal with the forces in this problem. So now what I'm going to do is I'm going to go through and I'm going to do the kinematics. So we're going to need to apply Newton's second law. And that requires us to do both kinematics and kinetics. So applying Newton's second law, we need to apply the force is equal to the mass times the inertial acceleration. So we're going to do the kinematics first. In the kinematics step, I have 2 rotations in this problem, which implies that I need 3 reference frames. Now those 3 reference frames in this particular case are going to be the following. I is the inertial frame, and it's the frame relative to which the track rotates. So the second frame is going to be the track itself, which is the cardioid. And the third frame, I'm going to call this third frame, I'm going to call it A. And now I have to look back at this picture a little bit to figure out what A is. Well, A defines the second rotation, which is defined by this angle theta. And the angle theta is measured from OQ to OP. So the plane that's rotating has one of its directions as OP. And now I need a direction normal to the plane of that rotation. So that direction normal to the plane of the rotation, which defines the direction OP, is normal to the plane of the track. And normal to the plane of the track is the OQ cross OP and OP plane. So this is equal to the OQ cross OP and then OP plane. Now, as we actually define that plane, it's easiest in this problem to work backwards in defining the coordinate systems. So in this case, I'm going to put the origin at O for all 3 of these coordinate systems. And then I'm going to define basis vectors. So for the basis fixed in the last frame, I'm going to put UR along OP. I'm going to put UZ along OQ crossed with OP. And then U theta is going to equal UZ crossed with UR. For the coordinates fixed to the track, I'm going to put the basis as EX is going to be along OQ. I'm going to say EZ is the same as UZ, which I just defined, and EY equals EZ crossed with EX. And then for this last one, I'm going to say that the basis that's fixed to the ground is going to equal little ex, little ey, little ez when t equals 0. So that's my basis. Now, given that I've done that, I can actually define the position of P relative to O. So the position of P relative to O is equal to R times UR. Now you'll notice that UR, U theta, UZ is fixed in A, and I need the rate of change in frame I. So in order to get the velocity and acceleration, we need to apply the transport theorem from A to I. So the first thing we need to do is we need to get the inertial velocity of point P, which is equal to the rate of change in frame I of the position of P relative to O, which is equal to the rate of change in A of the position of P relative to O, plus the angular velocity of A and I crossed with the position of P relative to O. Well, the rate of change in A of the position of P relative to O is equal to R dot times UR. Now I need the angular velocity of A and I. Well, that's equal to the angular velocity of T in I plus the angular velocity of A in T. The angular velocity of T in I is equal to omega, because the track rotates relative to the inertial frame with angular velocity omega, which is equal to omega EX. The angular velocity of A in T is equal to theta dot times UZ. which gives me that the angular velocity of A and I is equal to omega EX plus theta dot times UZ. But if you draw the picture here to be able to show what EX looks like in terms of UR and U sub theta, you wind up with UR U theta, and then you wind up with negative U theta here, and the angle theta is measured that way. So you can see that EX is equal to cosine theta UR minus the sine of theta times U sub theta, which leads to omega AI being omega cosine theta UR minus omega times the sine of theta times U theta plus theta dot times UZ. So now I can actually compute the second term in the transport theorem. Omega AI crossed with the position of P relative to O is equal to omega cosine theta UR minus omega sine theta U theta plus theta dot UZ crossed with R UR, which is equal to, and if we actually put this in the order of the basis vectors and do all the cross products, U theta crossed with UR is minus UZ, so I get plus R omega sine theta UZ, and then UZ crossed with UR is U theta, so I get R theta dot U theta, which gives that the inertial velocity is equal to R dot UR plus R theta dot U theta plus R omega times the sine of theta times UZ. Now if we take the next step and get the inertial acceleration is going to equal the rate of change in the inertial frame of the inertial velocity, which is equal to the rate of change in frame A of the inertial velocity, plus the angular velocity of A and I crossed with the inertial velocity. Now let's do this. D dt in A of the inertial velocity is equal to R double dot UR plus R dot theta dot plus R theta double dot U sub theta, and then because omega is constant I get plus omega times R dot sine theta plus R theta dot cosine theta times UZ. And that just comes from the fact that I was using that inertial velocity from before. And then the angular velocity of A and I crossed with the inertial velocity is equal to omega cosine theta UR minus omega sine theta U theta plus theta dot UZ crossed with R dot UR plus R theta dot U theta plus R omega sine theta UZ, which is equal to, and now UR crossed with U theta is UZ, so I get plus R omega theta dot cosine theta UZ, and then UR crossed with UZ is minus U theta, so I get minus R omega squared cosine theta sine theta times U theta, and then U theta crossed with UR gives me minus UZ, but then there's a negative sign, so I get plus R dot omega times the sine of theta times UZ, and then U theta crossed with UZ gives me minus R omega squared sine squared theta times UR, and then UZ crossed with UR gives me plus R dot theta dot U theta, and then UZ crossed with U theta gives me minus R theta dot squared times UR. So therefore, the inertial acceleration looks like R double dot minus R theta dot squared, and then minus R omega squared sine squared theta times UR. I get plus 2 R dot theta dot plus R theta double dot, and then the last term involving U theta is minus R omega squared cosine of theta times the sine of theta times U theta, and then the last term, you'll notice that you actually get in the UZ term, you got R omega theta dot cosine theta, but then you have another r omega theta dot cosine theta, and then you have the same thing for the omega r dot sine theta. You have two of them. So you get 2 omega r dot sine theta, and then plus you've got 2 omega r theta dot cosine theta times u z. So that should pretty much take care of the inertial acceleration. So what we can do at this point, because we're going to do this later on, is I'm going to say let AR equals the first component of this inertial acceleration, which is r double dot minus r theta dot squared minus r omega squared sine squared theta. I'm going to say a sub theta is equal to 2 r dot theta dot plus r theta double dot minus r omega squared cosine of theta times the sine of theta. And then I'm going to say AZ, there's a 2 in front of everything with the AZ, and then there's an omega. So we'll actually have 2 omega, and then what's left over is going to be an r dot sine theta plus an r theta dot cosine theta. So you can see that that gives me all of the terms involving the acceleration. And from this, I can actually write the inertial acceleration as a sub r ur plus a sub theta u theta plus a sub z times uz. And we'll use that later on in the derivations. So that takes care of the inertial acceleration. So I'm done with the kinematics. Now we're going to go on to the kinetics. So in the kinetics part of this problem, the first thing I need to do is I need to draw the free body diagram of the particle. So what are the forces that are acting on this particle? Well, let's see here. I have the force of friction, and I also have a normal force. I don't know what direction this normal force acts, but I have a model for it. I know that the normal force has two components, one along the principal unit normal and one along the principal unit binormal to the track. I also know that the friction force has the general form of minus B times ET, where B depends upon the type of friction. In the case of viscous friction, it's the coefficient of viscous friction times the speed relative to the track. That's for viscous friction. For Coulomb friction, it's minus mu times the magnitude of the normal. So I'm going to look at both of these in the process of doing this problem. So now let's actually go through this. So we know that the resultant force is equal to the normal force plus the friction force, which is equal to n sub n En plus n sub b Eb minus this coefficient b times the tangent vector, and that has to equal the mass times the inertial acceleration. So we have two different cases here. One, in the case of viscous friction, as we've seen previously, it's not necessary to know anything, to have any knowledge of the normal force. The reason that we don't need it is because the viscous friction model is in terms of the speed, and there's no unknown component of the normal force in that model. But for Coulomb friction, we actually need to know we need the knowledge of the, so we need to have the two components of the normal force in order to compute the magnitude of the normal force, And what do we need the magnitude of the normal force for? Well, we need the magnitude of the normal force because in order to substitute this magnitude into the tangential component, into the ET component of F equals ma to obtain the differential equation. Now that's really important because when we're dealing with Coulomb friction, it's a more complicated process from what happens when we're dealing with viscous friction. So these are the two situations that arise from each of these types of friction. So because I'm eventually going to need the intrinsic basis in order to do all the calculations, let's just go ahead and compute the intrinsic basis now, and then we'll use it in both viscous friction and Coulomb friction as we see fit for that particular part of the problem. So we need to compute or to determine the intrinsic basis relative to the track. So the first thing is that the tangent vector relative to the track is equal to the velocity as viewed by an observer fixed to the track divided by the speed relative to the track, where the speed relative to the track is the magnitude of the velocity relative to the track. So let's look at the velocity relative to the track. The velocity as viewed by an observer fixed to the track is equal to the rate of change in the track of the position of P relative to O. But the position of P relative to O is expressed in coordinates that are fixed in reference frame A. So this is equal to d dt in A of the position of P relative to O plus the angular velocity of A and T crossed with the position of P relative to O, which is equal to r dot times ur plus theta dot uz crossed with r which is equal to r dot ur plus r theta dot u theta. But if you look back over at the original expression, we have r and we have r dot. R is equal to b times 1 plus cosine theta, and r dot is equal to minus b theta dot sine theta. So now I can substitute those two results in here. This is equal to minus b theta dot times the sine of theta times ur plus b times 1 plus the cosine of theta. And actually, let's put this in the same order. It's b theta dot times 1 plus the cosine of theta times u theta when we finally put it all together. So now from that, I can actually compute the speed. So the speed is equal to the magnitude of the velocity, which is equal to, well, there's a b theta dot common to everything, so I can take it out. And that leaves me with sine squared theta plus 1 plus the cosine of theta squared, the whole thing raised to the 1/2, which is equal to b theta dot times sine squared theta plus 1 plus 2 cosine of theta plus cosine squared theta to the 1/2, which is equal to b theta dot times 2 plus 2 cosine of theta, which is equal to b theta dot times the square root of 2, there's a 1/2, times 1 plus cosine of theta to the 1/2. But if you recall, I actually did a substitution at the very beginning, or a trigonometric identity at the very beginning, where I used these, I did a little preliminary, and those preliminaries were as follows. I had that cosine 1 plus cosine of 2 alpha is equal to 2 cosine squared alpha. So let's use that result in here. So what have I got? I got 1 plus cosine theta. So if you look, I can actually replace theta. Suppose we say let theta equal 2 alpha. Then that makes 1 plus the cosine of theta equal to 1 plus the cosine of 2 alpha. But 1 plus the cosine of 2 alpha is what I had used earlier, which is 2 cosine squared alpha. So this becomes 2 cosine squared alpha. But because theta is equal to alpha over 2, that tells me that alpha is equal to theta over 2. So that I can use this result to give me 1 plus cosine of theta, which is 2 alpha. This gives me 1 plus cosine of 2 alpha, which is theta, is equal to 2 cosine squared theta over 2. I can now substitute that into the speed. So this gives me that the speed is equal to b times theta dot, and then there's a 1 plus cosine theta to the 1/2. 1 plus cosine to the 1/2. Theta to the 1/2 is the square root of 2 times cosine of theta over 2. There's another square root of 2. So I get 2b theta dot times the cosine of theta over 2 for my speed. So now what I can do is I can get the tangent vector. So then the tangent vector is equal to, well, it's equal to whatever I had in the numerator, which is this velocity. There's a b theta dot. So I get minus b theta dot times sine theta ur, and I get plus, I've got b theta dot times 1 plus cosine theta, and then this whole thing is multiplied by u sub theta, and it's divided by 2b theta dot times the cosine of theta over 2. But I can make another substitution here, which is that the sine of theta is equal to the sine of 2 alpha, which is equal to 2 times the sine of alpha times the cosine of alpha, which is equal to 2 times the sine of theta over 2 times the cosine of theta over 2. And then also using the fact that 1 plus the cosine of theta from before, we remember 1 plus the cosine of theta is equal to 2 cosine squared theta over 2. That gives me that the tangent vector can be written in the following form, which is the b theta dots cancel out. So I get minus 2 sine theta over 2 times the cosine of theta over 2 times ur, and then I get plus, I've got cosine squared theta over 2 times u sub theta, but then there's a 2 in there because I have to substitute the 2, all divided by 2 times the cosine of theta over 2. So then the 2 drops out, and I get that the tangent vector relative to the track is equal to minus the sine of theta over 2 times ur plus the cosine of theta over 2 times u sub theta. So that gives me the tangent vector. Now I need the normal vector. So let's actually compute the normal vector. So next, I know that En is equal to the rate of change of the tangent vector relative to the track divided by its magnitude. So I need the rate of change of the tangent vector relative to the track. Well, the rate of change of the tangent vector relative to the track is equal to the rate of change of the tangent vector in frame A plus the angular velocity of A and t crossed with E sub t. What's the rate of change in A of the tangent vector? Well, the tangent vector is expressed in terms of coordinates fixed in A. So this gives me minus theta dot over 2 times the cosine of theta over 2 times ur, and then the second term is a cosine, so I get minus theta dot over 2 times the sine of theta over 2 times u sub theta. What's the angular velocity of A and t crossed with the tangent vector? That's equal to theta dot uz crossed with, I've got minus sine of theta over 2 times ur plus the cosine of theta over 2 u theta, which is equal to, uz crossed with ur is u theta, and uz crossed with u theta is minus ur. So I get minus theta dot times the cosine of theta over 2 times ur minus theta dot times the sine of theta over 2 times u sub theta, which gives that the rate of change of the tangent vector as viewed by an observer fixed to the track is equal to minus 3 halves theta dot. And then if you look, if I can factor out a whole bunch of stuff here, I get cosine of theta over 2 times ur, and then I get plus the sine of theta over 2 times u sub theta. And you can see that what I'm adding, I've got negative theta dot over 2 minus theta dot gives me negative 3 halves theta dot, and that's true for both terms, which is why I get that. So now, the magnitude of this vector, because the magnitude of the vector that's in the parentheses is just 1, and so I get, and the negative sign, its magnitude is 1, this gives me 3 halves theta dot. So from this, I can actually get that the normal vector, which is equal to the rate of change of the tangent vector divided by its magnitude, is actually equal to, go to the next page, En is then equal to cosine theta over 2 times ur plus the sine of theta over 2 times u sub theta. And finally, we can compute EB. So finally, EB, which is equal to ET crossed with EN, is equal to, well, what's ET? ET is minus the sine of theta over 2 ur plus the cosine of theta over 2 u theta, and then this whole thing is crossed with cosine theta over 2 ur plus the sine of theta over 2 times u sub theta, which gives that the binormal vector, if I do the cross products, ur crossed with u theta is uz, u theta crossed with ur is minus uz, and so what we wind up with is we wind up with sine squared theta plus cosine squared theta equals 1. Actually, the normal vector is actually negative this because there's a minus sign in front of the whole thing. So this gives me a minus sign, and this gives me a minus sign, which actually gives me sine squared theta over 2 times Ez plus cosine squared theta over 2 times uz, and then uz, which is equal to u sub z. So there's my intrinsic basis. So my tangent vector is equal to minus the sine of theta over 2 times ur plus the cosine of theta over 2 times u sub theta. The normal vector to the track is equal to minus the cosine of theta over 2 times ur minus the sine of theta over 2 times u sub theta, and then the principal unit binormal is equal to uz. So now we have everything that we need in order to be able to get the differential equation. So now we're going to go through the two different types of friction. So let's do viscous friction. So for viscous friction, we know that the differential equation can be obtained by taking F dotted with ET is equal to the mass times the inertial acceleration dotted with ET. Now in this case, the friction force is equal to minus C times the speed. I already have the speed, I computed it from before. So F dotted with ET, which is equal to N plus F sub F dotted with ET, is equal to minus C times the speed relative to the track, because the normal force dotted with the tangent vector is 0. The mass times the inertial acceleration dotted with ET. Remember that I had written the acceleration in this general form, which was a sub r ur plus a sub theta times u theta. plus a sub z times uz, and that is going to be dotted with the tangent vector. But the tangent vector is equal to is dotted with that tangent vector. But that tangent vector is equal to minus sine theta over 2 ur. Actually, I have it right here. Minus sine theta over 2 ur plus the cosine of theta over 2 times u sub theta. So this gives me, well, if I take these components, I get minus m ar times the sine of theta over 2. And then I get m times a sub theta times the cosine of theta over 2, where ar and a theta are what I defined back when I finished the acceleration. So you remember that the acceleration was done up here, and I defined ar and a theta to be those two quantities right there, so I don't need to redefine them. So this gives me that minus c times the speed relative to the track is equal to minus m times the acceleration, the component in the ur direction, times the sine of theta over 2, plus m times the acceleration in the theta direction, in the u theta component, times cosine of theta over 2, where ar and a theta are as I defined them earlier. Now let's do the case for Coulomb friction. For Coulomb friction, what I had done was we said that the force was equal to the normal force plus the friction force, and in this particular case is different from what's here, because in this case we had the normal force, and now we have minus. And if you remember that the friction force was equal to minus mu times the magnitude of the normal times et, and that has to equal the mass times the inertial acceleration. So F dotted with et is equal to minus mu times the magnitude of the normal, and that has to equal, it's the same thing as what I got before, which is the mass times the inertial acceleration dotted with et. But I already computed the mass times the inertial acceleration dotted with et. It's what's sitting in the previous result. Minus m times ar, and then I've got sine of theta over 2, and then I've got plus m times a sub theta times the cosine of theta over 2. But the problem is here I have this unknown magnitude of the normal force, so I have to go through the other two components. So F dotted with En is going to equal n plus F sub F dotted with En, which in this case is going to equal n sub n, because that's my normal component, and that's equal to the mass times the inertial acceleration dotted with En. But that equals, well, what's the inertial acceleration? It's got three components, right? It's mass times the component in the ur direction plus the component in the u theta direction plus the component in the uz direction, dotted with this normal vector. But the normal vector is minus cosine theta over 2 ur, theta over 2 ur, minus the sine of theta over 2 times u sub theta, which is equal to, I get minus m ar cosine of theta over 2 minus m times a sub theta times the sine of theta over 2. And then that tells me that n sub n is equal to minus m ar cosine theta over 2, and then minus m times a sub theta times the sine of theta over 2. So that solves for the component along the En direction. The next thing is I need F dotted with EB. Well, that's equal to n plus F sub F dotted with EB. But again, just like En is normal to F sub F, EB is also normal to F sub F, so you wind up with n sub B, and that has to equal the mass times the inertial acceleration dotted with EB. But EB is equal to EZ, right? So this gives me that n sub b is equal to the mass times that inertial acceleration, which I had written in this general form. And this is dotted with EB, but EB is equal to UZ. So this says that the mass times the Z component of the acceleration is equal to n sub b. So now we have these two components of the normal force. N sub n is equal to minus m times AR and then cosine of theta over 2 plus a sub theta times the sine of theta over 2. And then n sub b is equal to m times the z component. So from this, I can get the magnitude of n, which is equal to n sub n squared plus n sub b squared to the 1/2. I use these two values. I substitute in here to get that. And then I can use that to be able to compute the differential equation, which gives me that minus mu times the magnitude of the normal is equal to, well, what's it equal to? It's equal to minus m, so I can factor the m out actually. It's m times minus AR times the sine of theta over 2 plus a sub theta times the cosine of theta over 2. And where does this come from? Well, this comes from the result that I just computed, which is that magnitude of that normal force. And this is the differential equation. So, of course, that's what happens in the case of Coulomb friction. In the case of viscous friction, I should have labeled it before, but this is the differential equation. And I didn't need to know anything about the normal force in order to be able to do the problem in the case of viscous friction. So we've just done this whole problem now using both Coulomb friction and viscous friction. And you can see that in the case of viscous friction, I didn't need to know anything about the normal force, but in the case of Coulomb friction, I did, and I solved for the two components of the normal force in the process of getting the differential equation of motion. And we're going to move on to another example in just a minute of a curve moving on a surface, and a particle moving on a surface. And so but I want to finish this by just, sort of re-emphasizing this point that when you're dealing with curves, it depends on the type of friction that you have, and you have to deal with whether or not you need to know the normal force or whether or not you don't need to know the normal force. In the case of viscous friction, you don't need to know that normal force. In the case of Coulomb friction, you actually do, and you need to determine the intrinsic basis in the process of doing that. So that's the end of this problem. We're going to now move on to a second example. The second example is going to be a particle moving while in contact with a surface. Now, the surface in this particular case is going to be a paraboloid. So I'm going to actually draw a paraboloid. Paraboloid kind of has this sort of a bowl-like a shape. It's a parabola, basically, that's been revolved. And what I'm going to do is we're going to actually describe this the equation for the paraboloid in the following way, which is that I have a particle that's moving while in contact with this paraboloid. The particle is located on the inside surface of the paraboloid. And what I'm going to do is I'm going to describe the location of the particle P, which has mass m, in terms of a distance r, where r is the position of a point, is the distance from a point Q to a point O in the horizontal plane, and then there's an angle theta, which describes the orientation from an inertially fixed direction, which I'm going to call this inertially fixed direction EX, and then the in-plane in the horizontal plane is EX, EY, and the normal to that plane is EZ. So the equation for this is Z is equal to R squared over 2B. That's the equation for the paraboloid. Now, I'm going to assume again in this problem that that there's friction. So we're going to assume friction, and we're going to deal with both types of friction. So we're going to deal with both Coulomb friction, viscous friction, and Coulomb friction. And I'm going to do this problem using the appropriate kinematic steps and the appropriate kinetic steps. So the goal here, as it was before, in this case, because we're dealing with a surface, the objective is to determine a system of two differential equations of motion for the particle in terms of r and theta. It's going to be a system of two equations. So we're going to have to do all the things that are associated with a surface in this particular case. So the surface is a paraboloid, and I'm going to assume that it's inertially fixed. So assume the surface is inertially fixed. It'll just make things a little bit easier when we actually go through the rest of the analysis. So we need to apply F equals ma. So we're going to need to apply F equals the mass times the inertial acceleration. So S is equal to the surface, which is the inertial reference frame. Now, let's go through and do this problem. We have one rotation, so we're going to do the kinematics first. So we have one rotation. We have one rotation, which means we need two reference frames. Now in this particular case, S is the inertial frame. And then we're going to define a second frame, which I'm going to call A, and it's going to be the plane defined by EZ and OQ. So it's the EZ OQ plane. And again, I'm going to work my way backwards. In this case, it doesn't really matter that much because there's only one rotation, so it's not as complicated as it was in the previous problem. But we're going to go through this the same way. ER is going to be along OQ. I'm going to say EZ is equal to the basis vector EZ, which was given. And then E theta is equal to EZ crossed with ER. Here I've got the origin at O, and then the basis EX, EY, EZ is given. I drew it in the problem description. So now the position of P relative to O is equal to the position of Q relative to O plus the position of P relative to Q, which is equal to R ER plus Z EZ. Now Z is equal to R squared over 2B, so this gives me that the position of P relative to O is equal to R ER plus R squared over 2B EZ. So now to get the inertial acceleration, I first have to get the inertial velocity, which is equal to the rate of change in S of the position of P relative to O, which is equal to the rate of change in A of the position of P relative to O, plus the angular velocity of A and S crossed with the position of P relative to O. Well, that's equal to R dot ER plus 2R R dot over 2B, so the 2 drops out. So you get R dot over B EZ plus the angular velocity of A and S is theta dot EZ crossed with R ER plus R squared over 2B EZ, which is equal to R dot ER plus R dot over B EZ plus R theta dot E theta, which gives R dot ER plus R theta dot E theta plus r dot over b ez. That takes care of the velocity. The acceleration is equal to the rate of change in the inertial frame, which is s, of the velocity of point P as viewed by an observer in the inertial frame, which is equal to d dt in A of the velocity of P in S, plus the angular velocity of A in S crossed with the velocity of P in S, which is equal to r double dot ER plus r dot theta dot plus r theta double dot times E theta plus r dot squared plus r double dot over b ez plus theta dot ez crossed with r dot er plus r theta dot e theta plus r dot over b ez, which is equal to, if we go through this, well, ez crossed with er is e theta, and ez crossed with e theta is minus er, so I get r double dot minus r theta dot squared er plus, I've got the terms involving e theta, which is 2r dot theta dot plus r theta double dot e theta, and then I have the term involving ez, which is r dot squared plus r double dot all divided by b, and then this is multiplied by ez. Now I have the acceleration as viewed by an observer in the inertial frame. So I'm done with that, and this should actually be in S. Acceleration as viewed by an observer in the inertial frame. So now I have that. So now I'm going to do the kinetics. So the kinetics in this problem, let's assume, like I didn't put this in the problem, but let's just assume gravity acts downward. Okay, so we're going to put gravity in the problem this time. So you can see that the free body diagram for this particle has the following features, which is that there's the force of gravity acting downward, there's a normal force, and then somewhere in here, which I have to figure out its direction, is a friction force. So the normal force in this particular case is equal to n times n, because I'm dealing with a surface. Well, remember that n is equal to the gradient of the function that defines the surface divided by its magnitude. The friction force has two components, which are that there's going to be a friction force in the T1 direction and the T2 direction, and it depends on what the model is. But in the case of either of these models, I'm going to get one of two things. So in this case, it's actually a little bit more complicated from what it was for a curve. So let's actually write this down. So the friction force is going to equal, in the case of viscous friction, it's going to equal minus c times the velocity as viewed by an observer fixed to the surface. That's for viscous friction. And then for Coulomb friction, it's going to be minus mu times the magnitude of the normal times the velocity of p as viewed by an observer fixed to the surface divided by its magnitude. And this is for Coulomb friction. Now, given the fact that I'm doing both of these types of friction, I have to separate these two out and deal with this. But let's write the gravity force. mg is equal to minus mg times ez. So now I have the gravity force. So now I know that the force is equal to the normal force plus the friction force plus the gravity force, and that has to equal the mass times the inertial acceleration. So you can see that now in the case of these two different types of frictions, I'm going to need two differential equations. There are two components along which I'm going to need to get differential equations. So I have to go through, and I now have to deal with the different types of friction. So in this case, what I have to do is we need to construct a basis. I'm going to call that basis T1, T2, and N, where T1 and T2 lie in the tangent plane to S at P, and n is already the unit normal. So n is the unit normal to the tangent plane to S at point P. So I'm almost there. I have to construct this basis, and we'll be able to get the rest of this done. So the first thing I need to do is I need to construct n. So the function that defines the surface in this case is a function of r, theta, and z, and it's equal to r squared over 2b minus z, which is equal to 0. So the gradient of this is equal to the partial of f with respect to r times er plus 1 over r, the partial of f with respect to theta times e theta, plus the partial of f with respect to z times ez. That's in cylindrical coordinates. So this gives me r over b times er, and then minus ez, which tells me that the magnitude of the gradient is equal to r squared over b squared plus 1 raised to the 1/2. So we can actually now write the unit normal. The unit normal is then equal to, well, it's equal to the gradient of f, which is r over b er minus ez, all divided by r squared over b squared plus 1 raised to the 1/2. So if I multiply numerator and denominator through by b, I get RER minus BEZ, all divided by r squared plus b squared to the 1/2. That is my normal to the surface. Now you'll notice something, that I can actually construct a vector immediately that's orthogonal to this, that's going to be in the tangent plane. Notice that n does not have a component in the e theta direction, right? And because it doesn't have a component in the e theta direction, that means n dotted with e theta has to equal 0. So that tells me that e theta must lie in the tangent plane to S at P. And the reason it has to lie in the tangent plane is because n is normal to that tangent plane, and if I find a vector that's orthogonal to n, it has to be in the tangent plane, right? So I can say, let T1 equal E sub theta. So then I can get T2 straight away. So then T2 can be given as, if I say n is the third vector and T1 is the first vector, it's n crossed with T1, which is equal to the vector n that I just constructed, which is RER minus BEZ, all divided by r squared plus b squared to the 1/2, crossed with E sub theta, because E sub theta is my first vector. And so what do I get? Well, I have an r squared plus b squared to the 1/2 in the denominator, and I've got ER crossed with E theta is EZ, and EZ crossed with E theta is minus ER, so I get B ER and then plus REZ. Now we can actually check again that these vectors form a right-handed orthonormal system, and we can do that simply by taking a cross product. So what we can do is we can say, what's T1 crossed with T2? Well, T1 crossed with T2 is E theta crossed with, I've got BER plus REZ, all divided by r squared plus b squared to the 1/2, which is equal to, well, I still have an r squared plus b squared in the denominator to the 1/2 in the denominator when I'm all done. And what do I get? Well, E theta crossed with ER and E theta crossed with EZ. Well, E theta crossed with EZ is ER, so I get R, ER. And then E theta crossed with ER is minus EZ, which is equal to N. So as a result, I find that T1, T2, and N is a right-handed orthonormal basis. So T1, T2, N is a right-handed orthonormal basis and T1, T2 lies, or I should say spans, the tangent plane to S at P, while N is normal to the tangent plane to S at point P. So we're almost done here, because now what I can do is I can look at each of the cases of viscous friction and Coulomb friction. So let's do viscous friction first. So for viscous friction, I know that the force of friction is equal to minus c times the velocity as viewed by an observer fixed to the surface. What's the velocity as viewed by an observer fixed to the surface? I already did that. It's equal to r dot er plus rr dot over b plus r theta dot e theta. So this gives me minus c times r dot er plus rr dot over b e theta plus, sorry, make sure I do this in the right order, r theta dot e theta plus rr dot over b ez. So then F, which is equal to n plus F sub f plus mg, which is equal to nn, and then minus c times this velocity relative to the surface minus mg ez, that has to equal the mass times the inertial acceleration. So I can get the two differential equations now straight from the two components along T1 and T2. F dotted with T1 is equal to n plus F sub f plus mg dotted with T1, which is equal to, well, n dotted with T1 is 0, and I get minus c times the speed times T1, and then I get, and then I also get minus mg ez dotted with T1. But T1 was equal to e theta. So this gives me that F dotted with T1 is equal to minus c. So if I take the dot product with e theta, what do I get? I get the second term, so I get minus c. I get r theta dot, and that gives me, that's dotted with T1. So remember that T1 is equal to e theta. Just remind ourselves of that. And then ez dotted with e theta is equal to 0. So this gives me minus c r theta dot is equal to, and that has to equal the mass times the inertial acceleration dotted with T1, which is equal to the mass times the inertial acceleration dotted with e theta, which gives me that minus c r theta dot is equal to the mass, and then the inertial acceleration dotted with e theta. If I look back at the inertial acceleration, I have the e theta component as 2 r dot theta dot plus r theta double dot. 2 r dot theta dot plus r theta double dot. That's the first differential equation. Now, we can get the second differential equation from the fact that F dotted with T2 is equal to n plus F sub f plus mg dotted with T2. That's equal to, well, n dotted with T2 is 0. I get minus c times the speed, times the velocity dotted with T2, and then I get plus, so minus mg ez dotted with T2. But what's T2? T2 has two components. It's got an ER component and an EZ component. So I can do these. And if I take this velocity, I need the ER and the E theta components. I've got minus CR dot. So I've got minus C times R dot. And then T2, I've got to get the ER component, which is B. So I'm going to wind up manipulating this a little bit to make it a little bit easier on myself. And then I've got the E theta component, sorry, the EZ component. I've got an REZ, so I need the EZ component of the speed, which is RR dot over B. So I've got plus R squared R dot all divided by B. And then I've got minus mg EZ dotted with T2. But T2 has a component, so it's minus mgr and then this whole thing is divided by r squared plus b squared to the 1/2. And that has to equal the mass times the inertial acceleration dotted with T2, which is equal to, well, the inertial acceleration dotted with T2 gives me the mass, and I get r double dot minus r theta dot squared. That's the first term, right? And then I've got times T2 again. Let's go back and get T2. There's a B, and then I've got a B, and then I've got plus, and now I've got r dot squared plus r double dot all divided by B, and that whole thing is multiplied by r. And then I'm dividing this whole thing by r squared plus b squared to the 1/2. So my second differential equation, if I simplify it, because everything here is being divided through by that r squared plus b squared, I get the second differential equation, which gives me minus c times r dot times b. And then I've got plus r squared r dot all divided by b, and then minus mgr, and that has to equal what's on the other side, m times r double dot minus r theta dot squared times b, and then plus I've got r dot squared plus r double dot times r all divided by b, and that is the second differential equation. And that's for the case of viscous friction, which is what I started with over here. So we're doing viscous friction, and there's viscous friction right there. So now for the case of Coulomb friction, things get a little bit more complicated. So for the case of Coulomb friction, my model is that this friction force is minus mu times the magnitude of the normal times the velocity as viewed by an observer fixed to the surface divided by its magnitude. And so that tells me that the total force, which is equal to N plus F sub F plus mg, which has to equal the mass times the inertial acceleration. Now I've got a little bit more work that I have to do, which is that you can see that if I take F dotted with ET, what do I get? I get N plus F sub F plus mg dotted with not ET, with T1. And this is dotted with T1, right? But T1 is equal to E theta, and it's also normal to N. So I get minus mu times the magnitude of the normal times the velocity as viewed by an observer fixed to the surface dotted with T1, all divided by its magnitude. And you can also see that when I do this, that because T1 is equal to E theta, just like I had before, mg dotted with T1 is equal to 0. And so this has to equal the mass times the inertial acceleration dotted with T1. But I have an unknown component of reaction force there. I have to figure out what that is. The same thing goes for the T2 component. F dotted with T2 is equal to, well, I go through the same argument. I get minus mu times the magnitude of the normal times VPS dotted with T2, all divided by its magnitude, and then that has to equal the mass times the inertial acceleration dotted with T2. So as a result of doing this, I have to figure out, so we need the magnitude of n. But the magnitude of n in this case is obtained by taking f dotted with n. F dotted with n is equal to n plus f sub f plus mg dotted with n, which is equal to the component n, and then f sub f is normal to n, and I get minus mg ez dotted with n. But what's n equal to? If we go all the way back to the beginning, we figured out what n was. So n is equal to RER minus BEZ all divided by that square root. So this leaves me with n minus mg, and then if I go back again, so I need n, I've got the EZ component. So I got minus mgr, mgb, so I've got mgb, but then there's a negative sign, all divided by r squared plus b squared to the 1/2. That's f dotted with en, and that has to equal the mass times the inertial acceleration dotted with en, which is equal to, I've got the mass, and then I've got r double dot minus r theta dot squared, and then I'm multiplying by n, and then n again is equal to, what have I got? I've got RER minus BEZ, so I've got r, and then I've got minus r dot squared plus r double dot, all divided by b, and then this is multiplied by b, and then this whole thing is divided by r squared plus b squared to the 1/2. And so from this I can now solve for n. So therefore, n is equal to, I've got m times r double dot minus r theta dot squared, and then times r, and I got minus m times r dot squared plus r double dot all divided by b, and that's multiplied by b, so the b actually winds up canceling out. So I just get m times r dot squared plus r double dot, all divided by r squared plus b squared to the 1/2, and then I have minus mgb and that's all divided by r squared plus b squared to the 1/2. So then the magnitude of n is equal to the absolute value of this result, and it's actually the absolute value of this. And as a result, then I can substitute into the T1 and T2 components to get the differential equations. So the T1 and T2 components, we remind everybody, we got minus mu times the magnitude of n, all divided by VPS dotted with T1, all divided by its magnitude. And that has to equal the mass times the inertial acceleration in the T1 direction. So that's equal to the mass times the inertial acceleration in the T1 direction, but T1 is equal to E theta, so this is equal to m times 2r dot theta dot plus r theta double dot. The second one is minus mu times the magnitude of the normal times VPS dotted with T2, all divided by its magnitude, is equal to the mass times, now I've got to do this for the T2 direction, but the T2 direction, we remind everybody that the T2 direction is equal to BER plus REZ divided by that square root. So we wind up here times m times r double dot minus r theta dot squared times b, and then I get plus m times r dot squared plus r double dot all divided by b times r, and this whole thing is divided by r squared plus b squared to the 1/2. And in both of these cases, I need to substitute the result of the magnitude of n into this, and I get the two differential equations. So these become the two differential equations. And so as a result of them becoming the two differential equations, I see that I needed to know the normal force in order to be able to compute the two differential equations. So in this latter case, I had to know the normal force. So we actually have now studied two complete examples where we've actually gone through the details of this, and we've computed the differential equations in both cases. One for a particle sliding on a curve, and one for a particle sliding on a surface. And the only step I didn't do in this last problem is I didn't take the dot product of VP with T1 and VP with T2. But I can do that just to complete this. So VPS dotted with T1 is equal to, well, if you remember what the velocity was, just go back over here and we'll do this, is that the velocity as viewed by an observer fixed to the surface was equal to r dot er plus r dot over p. I need the component in the e theta direction. So I've got VP dotted with T1 is equal to r theta dot, and then I've got times T1, which is equal to E theta. So that's VP dotted with T1. VPS dotted with T2 is equal to R dot, and then this is actually times R dot times, now I've got T2, and I remember what T2 is. T2 was equal to BER plus REZ. So I get a B in this result, which gives me R dot times B, and then I also have another component, BER, and then I get R dot all divided by B times R, which gives me an R squared all divided by R squared plus B squared to the 1/2. And then these two results can be substituted into the previous two results here to be able to give me the differential equations. And of course I can compute the magnitude of this too, which is the magnitude of VPS is just equal to R dot squared plus R squared theta dot squared plus R squared R dot squared over B squared, the whole thing raised to the 1/2. So we've just finished two examples, and we figured out the differential equations in both cases for a particle sliding on a curve and a particle sliding on a surface. And we'll do more examples in the future.